If you could step through a black hole, what exactly would be on the other side? Most people imagine a tunnel, a mouth on this end, an exit on the far end, and some hidden place waiting behind the darkness. But today isn't a black hole's 101. This is one precise question. What does other side actually mean in physics? Because in general relativity, the universe doesn't come with a single reliable map. The words inside and outside depend on how space-time is drawn. In one set of coordinates, the event horizon looks like a lethal cliff where time freezes and reality snaps. In another, it's a perfectly ordinary boundary you can cross without noticing, at least for a moment. And if you keep changing the map carefully, mathematically, you start to see strange shapes appear. Einstein-Rosen bridges that resemble wormholes, white holes that behave like time-reversed black holes, and even regions that look like other universes on the page. But here's the uncomfortable twist. Some of those other sides might be as real as a country that exists only because your atlas was folded a certain way. So stay with me. By the end, you won't just hear rumors about parallel universes. You'll understand why mathematics can produce a clean, dramatic other side in ideal models. Why real astrophysical black holes likely ruin the fantasy. And why the most amazing thing we find beyond the horizon might be the edge of our own understanding. Maybe the most honest way to continue is to slow the question down until it almost falls apart in your hands. Not to rush toward whatever might be lurking beyond the darkness, but to ask very carefully what kind of beyond we are even talking about. When most people picture the other side of a black hole, they imagine something very familiar: a tunnel, a mouth on our side, an exit somewhere else, and a hidden corridor threaded through the middle. Films lean into that intuition. In the movie Interstellar, which premiered in Los Angeles on October 26, 2014, the black hole and its wormhole cousin are staged almost like props in a cosmic train station. You go in here, you come out there. It is a powerful image. It makes the universe feel navigable. It gives the word side a comforting spatial meaning, the way a bridge has two shores. Physics does not let us begin the question that simply, because to even ask what lies on the other side, you are already doing something subtle. You are treating space-time itself as if it were a stage with front and back doors. You are imagining that there is a global outside and a global inside that everyone can agree on. And that is exactly what general relativity takes away from you. Einstein's theory does not describe gravity as a force pulling at a distance. It describes it as the shape of space-time itself. Every event in the universe, every tiny here and now, is a point in that four-dimensional fabric. To talk about where something is, or when something happens, we choose a set of coordinates, like lines of latitude and longitude on a globe, and we write its position in numbers. But the coordinates are not the thing. They are just labels we paint on the territory. If you have ever looked at a map of Earth and noticed Greenland swollen to the size of a continent, you know what can go wrong when you confuse the map for the world. Some projections stretch the poles until they look like impossible walls. Sail far enough north, and the coastline on the paper seems to run off to infinity. Of course, if you were actually walking there, nothing special would happen. You would not fall off the page. The distortion lives in the map, not in the ground beneath your feet. General relativity is full of these cartographic tricks. On November 25, 1915, when Albert Einstein presented his gravitational field equations to the Prussian Academy of Sciences, he handed physics a new kind of world atlas. From that moment on, any honest conversation about an other side of anything gravitational had to be translated into geometry. Not just a picture of stuff moving in space, but a picture of space and time themselves, curved and intertwined by matter and energy. A few months later, in 1916, Carl Schwarzschild found the first exact solution to those equations for the space, around a perfectly spherical, non-rotating mass. On paper, this looks simple. a radial coordinate, a time coordinate, and some angular coordinates describing directions on a sphere. The solution would, much later, become the seed of what we now call a black hole. It also planted the first illusion that there was some hard tear in reality at a particular radius. The place where the radial coordinate, often called r, takes a special value proportional to the mass, the famous Schwarzschild radius. In those original coordinates, when r is equal to twice the mass parameter m, the mathematical expression seems to blow up. Denominators go to zero. Components of the spacetime metric diverge. On the page, it looks as if spacetime itself is cracking at that radius. If you take that picture too literally, you might say, here is a wall. Everything on one side is outside, everything on the other side is inside, and the wall itself is somehow the dangerous border between reality and its breakdown. But just as Greenland is not actually the size of Africa, the apparent catastrophe at that radius may be hiding a simpler story. That blow-up can be a coordinate singularity, not a physical one, a symptom that the particular labels we chose are bad at describing the region near the Schwarzschild radius, the way certain map projections are bad at describing the polar regions of Earth. This is where the phrase "other side" starts to get slippery. If the map itself is breaking at the event horizon, what exactly are we pointing to when we say the other side of the horizon? Are we talking about a real invariant feature of spacetime, something every observer in every coordinate system would agree is there? Or are we talking about a ghost created by the way we chose to draw the grid? General relativity gives us a more disciplined language for this. Instead of asking naively what is beyond some surface, we ask what happens to geodesics. A geodesic is the straightest possible path in curved spacetime. Free-falling particles follow time-like geodesics. Light follows null geodesics. These are the lines that tell you what future means for anything that is not firing its rockets. So the question, is there an other side, quietly becomes, do these geodesics, these paths that represent lawful motion, extend smoothly through the region we are worried about? Or do they simply stop, with no way to continue them in any reasonable fashion? If they can cross the horizon without any local drama, then the horizon is not a tear in the fabric. It is a causal boundary, a surface that separates regions with different futures, but not a solid wall you collide with. This is not how black holes entered popular imagination. By the late 1960s, as mathematical relativists were drawing ever more comprehensive diagrams of spacetime, a different kind of storyteller was at work. John Wheeler, a theoretical physicist with a flair for language, helped popularize the term black hole. The phrase is simple, evocative, and slightly terrifying. It conjures the image of a cosmic mouth that swallows everything, including light, and never lets it return. The metaphor stuck. From then on, the public picture of a black hole was not a region of spacetime with a subtle causal boundary. It was a pit in the universe, a kind of bottomless drain. Meanwhile, in the mathematics, something more abstract was unfolding. People were studying the global structure of spacetime solutions, not just their local behavior. They were asking, if I take this solution and push it as far as possible, extending every geodesic I can, what entire manifold do I get? Are there regions that my first choice of coordinates never showed me? The way a local street map never tells you the shape of the whole globe? In that context, the words inside and outside started to look provisional. They depended on which chart of the atlas you were using. Change the coordinates, and surfaces that had looked singular became smooth. Points that seemed unreachable appeared as ordinary locations on some new page. And new regions, what looked on paper like entirely separate universes, emerged as parts of a larger, completed spacetime. For someone standing on Earth, looking up at the night sky, this can feel unnecessarily abstract. You might be tempted to say, fine, but when I ask what is on the other side of a black hole, I mean something simple. I mean, if I fall in on Monday, what place do I emerge from on Wednesday if I ever do? Or if I could somehow look through, what would I see? Another galaxy? A newborn cosmos? A blank, unknowable void? The harsh answer is that physics will not let us hold on to that simplicity without cheating. Because in general relativity, there is no single privileged way to slice space-time into moments and places. Your Monday and my Monday are not globally defined surfaces we can both agree on, unless space-time has very special symmetries. In the strong gravity regime, near and inside a black hole, our intuitions about before and after, over here and over there, simply stop being reliable guides. The coordinates that feel natural to you as an outside observer are not the ones that feel natural to someone falling in. Their clocks, their notion of simultaneity, their picture of what counts as the other side will not match yours. So before we can say anything honest about what might exist beyond an event horizon, we have to make a quiet decision. We have to choose which question we are really asking. Are we asking whether there is another spatial region, disconnected from ours, that some idealized extension of the equations happens to contain? Are we asking whether an infalling astronaut experiences a continuation of their world line past the horizon with a well-defined future? Are we asking whether our universe's space-time, with its real history of collapsing stars and accretion disks and mergers, contains any region that could fairly be called a second exterior, a different cosmos? Or are we, without noticing it, asking the map to tell us something about itself instead of about the territory? From here on, the tone of the journey has to stay clear. We will not only ask, is something there? We will keep asking, under what map? Under what assumptions? Does this question even make sense? That is less glamorous than a promise of shortcuts to other universes, but it is also more faithful to what the equations are actually telling us and to what they refuse to say. And if we want to see any kind of other side appear without fooling ourselves, the first thing we must repair is our broken drawing of the horizon itself. The way we choose to lay out time and space around a black hole, and the stories those choices quietly smuggle into our imagination. So instead of staring at the horizon from afar, imagine we simply let go and fall, not as an abstract point on a diagram, but as a body with a heartbeat, a clock on the wrist, and a brief memory of the stars above. Picture an astronaut floating in the quiet darkness near a very massive black hole. There is no dramatic music, no glowing grid in space, just the slow curve of starlight and the distant shimmer of a warped accretion disk. The engines are off, thrusters silent. The astronaut has committed to free fall, trusting only the equations and their suit's instruments. As the orbit decays, they drift inward. At first, nothing feels different from falling toward any other massive object. Gravity is a tug, not a tear. The black circle ahead grows larger, its edge soft with light that has been bent and dragged around it. Somewhere in the mission briefing, a line stuck. At the so-called Schwarzschild radius, this r equals twice the mass parameter. Something important happens. A horizon. A point of no return. You might expect an audible click, a shudder in the hull, some sign that a cosmic border has been crossed. But in the astronaut's own frame, nothing of the sort occurs. Their onboard clock keeps ticking steadily. The heart rate monitor shows the same slow rise of adrenaline it would in any dangerous descent. The fabric of the suit does not strain or snap. If you could somehow erase the view outside and only show them the readings of local physics, they would not be able to say, from those alone, this exact moment is when I crossed the event horizon. From their point of view, the crossing happens in a perfectly finite interval of proper time. They begin outside. They fall. A calculable time passes on their wristwatch. They are now inside. No wall, no impact, no sense of touching anything. The drama that so many popular images associate with the horizon lives not in the local experience of the faller, but in the coordinates of the distant observer. In the classic Schwarzschild coordinates, the time variable we call t behaves strangely near the horizon. As the infalling astronaut approaches that critical radius, the equations that describe their motion, written in those coordinates, say it takes longer and longer coordinate time to get closer. The light signals they send outward take an ever harder path to escape the deepening gravitational well. Each pulse is stretched in wavelength, Red-shifted, weakened. If you are far away, sitting beside a telescope and watching the signals arrive, you see the story unfold very differently. Each new image of the astronaut takes longer to reach you. The rhythm of their clock slows down. Their motions appear more and more sluggish. The light you receive shifts redder, fainter, smeared over longer intervals. In the limit, as the astronaut's world line crosses the horizon in its own frame, the corresponding coordinate time in yours tends to infinity. In that picture, they never quite reach the horizon. They seem to freeze, painted as a dim ghost on the edge of darkness. It is tempting to say, there is the wall. Time stops there. That frozen ring of almost falling is proof that the horizon is a kind of solid surface. But what you are seeing is not a physical barrier. It is a coordinate effect. Schwarzschild time t is a choice we made to label events, one that works well far from the black hole but behaves badly near the horizon. The blow-up of t at that radius is a sign that this particular labeling scheme is failing, not that the universe itself has come to a halt. If you switch to another set of coordinates, better adapted to the behavior of light and infalling matter, the mathematical singularity at the horizon simply disappears. The metric, the object that tells you about distances and times, becomes smooth there. The fall continues. This insight was clarified in the mid-20th century. Arthur Eddington had already played with alternative coordinates in the 1920s, looking for ways to describe light rays moving in curved spacetime more cleanly. But it was David Finkelstein, in a short paper published in the late 1950s, who framed the event horizon of a Schwarzschild black hole in a way that changed the conversation. In 1958, Finkelstein showed that the apparent singularity at the Schwarzschild radius is in fact a coordinate singularity. By introducing a new time coordinate built from the paths of light, he constructed a chart in which the horizon is locally completely ordinary. No physical quantity blows up there. Free-falling observers cross it in a finite proper time, just as our astronaut's wristwatch suggests. What Finkelstein emphasized is that the horizon is not a place where the universe tears. It is a causal boundary, a one-way membrane in the structure of spacetime. Outside this boundary, there are future-directed paths that lead away to infinity. Inside, every possible future-directed path, for both matter and light, points deeper inward. The asymmetry is not between before and after in some absolute sense, but between what kinds of futures remain open once you have crossed. This is easier to picture if you imagine the light cones that relativity assigns to each event. At any point in spacetime, the speed of light defines a cone of allowed directions for causal influence. Inside the cone are time-like directions, the possible world lines of massive objects. On the surface of the cone are null directions, the paths of light. Outside, the cone lie directions that would require faster-than-light travel, forbidden by the theory. Far from a black hole, these cones are oriented in a way that feels intuitive. Some forward-tilting directions correspond to moving into the future while heading outward in space. Others tilt toward the mass. You can choose, by firing your rockets in one way or another, whether your future path leads you closer to the gravitational source or farther away. As you approach the event horizon, the cones themselves begin to tip. Close to the horizon, but still outside, there remain future-directed null directions that point outward. If you start in just the right way, you can still send a beam of light that escapes to infinity. There are still time-like world lines, the possible paths of spacecraft and people that curve outward and never fall in. Cross the horizon, and the geometry rearranges these possibilities. Inside, the light cones tilt so far inward that every future-directed null direction points deeper toward the center. The time-like interior of each cone, the region of allowed massive motion, is squeezed in the same way. No matter how you fire your rockets, no matter what effort you make, every path that respects the speed of light and causality leads you closer to the singularity. The horizon has not appeared as a surface you can bump into. It has appeared as a change in the shape of time. Inside is no longer merely a location. It has become a compulsory future. From the astronaut's perspective, there is a clear before and after to the crossing. Before, there existed choices of motion that could, in principle, carry them back out. After, there are none. Yet at the exact moment of crossing, the local experience remains smooth. The curvature of spacetime is strong but finite. Tidal forces may already be noticeable, but they do not suddenly jump to infinity at the horizon itself. Those catastrophes, if they come, are reserved for the deeper interior. The distant observer, meanwhile, never witnesses the crossing directly in their original coordinates. They see a continuous story whose images fade and slow, the light redshifted beyond detection. The causal structure of spacetime conspires with the choice of Schwarzschild time to hide the act of crossing behind an infinite stretch of coordinate duration. It took real astrophysical systems to make this less of a mathematical curiosity and more of a physical conviction. In the mid-1960s, astronomers identified a remarkably bright X-ray source in the constellation Cygnus. It became known as Cygnus X1. Over time, careful observations of its companion star's motion and the properties of the X-ray emission pointed toward an object with too much mass in too small a volume to be any known kind of neutron star. The best explanation, increasingly accepted as the data accumulated, was that this system harbored a black hole. Objects like Cygnus X1 do not carry labels saying here is an event horizon. We infer their existence by the behavior of matter and radiation around them, by the absence of any solid surface signatures in the observed signals. But each such inference tightens the idea that the horizon is a real, causal boundary in nature. It is not just a mathematical trick. It is also not a hard surface. There is no flash when you cross it, no bouncing. Only the quiet transition from a region where escape is in principle possible to a region where escape is no longer part of the future. Seen this way, the other side of the horizon does not first mean another place in space. It means another domain of possible futures. Outside, you can imagine world lines that wander, orbit, or flee. Inside, every world line that respects relativity's rules ends at the singular region in the finite proper time of the traveler. That inward future is the first and most reliable other side we can talk about. And it is already more unsettling than the cinematic idea of a tunnel. It is not a door you walk through and then choose your next destination. It is a boundary you cross once, after which the range of futures collapses. For a human sitting at a screen, this is harder to feel than a glowing ring in space. We are used to thinking of geography in terms of surfaces and walls, not in terms of the tilting of light cones and the narrowing of causal options. But the physics insists. From the standpoint of local measurements, the horizon is ordinary. The extraordinary thing is what it does to the global shape of histories. If you accept that, you have already taken a quiet step. You have let go of the idea that the other side is a place with rooms and vistas waiting to be explored. You have started to see it as a region of spacetime where the future is rearranged so drastically that returning to the outside universe is no longer a possibility, however clever the technology or determined the will. That is a difficult kind of other side to visualize. Our diagrams will try to help. We will stretch and compress coordinates, introduce new variables that tame the bad behavior of the old ones, and draw pictures where light rays become straight lines and horizons appear as clean boundaries rather than places where equations blow up. But each of those choices is still a kind of ruler we lay across space-time. Each ruler has its limits. The Schwarzschild time coordinate, with its misleading freeze at the horizon, is one such ruler. To describe the crossing and the interior more honestly, we will need a different measure of distance, one that captures how space itself stretches near the horizon without turning that stretching into an illusion of an impenetrable wall. A peculiar, patiently named coordinate waits for us there. A coordinate that, like the fable of Achilles and the tortoise, turns the last steps toward the horizon into an infinite sequence on paper, even as the falling astronaut reaches it in finite time. To see how that works and why it matters, we have to change our ruler. The first new ruler looks deceptively simple. It changes nothing in the astronaut's experience, and yet it stretches the horizon so far away on paper that, In a sense, it never quite arrives. It is a reminder that you can distort a journey with nothing more than a choice of coordinates. In the original Schwarzschild chart, the trouble shows up most clearly if you try to follow the paths of light near the horizon. Radial light rays, which ought to be your simplest guides to causal structure, start to behave awkwardly as you approach the critical radius. The equations that say how t, the Schwarzschild time, and r, the radial coordinate, relate along those light paths become unpleasant. They suggest that, according to this clock at infinity, it takes an endless amount of time for anything to reach the horizon. To tame this, relativists introduce a new way of measuring the radial direction. They keep the usual r as a label on the spheres around the black hole, but they define a new coordinate, usually spoken of as r star, the Tortoise Coordinate. It is built in such a way that light rays moving radially, inward or outward, have a simple form when expressed in terms of t and r star. The name is not an accident. This coordinate behaves like the usual radial distance far away from the black hole. But as you get closer to the horizon, it slows down, stretching the last part of the journey into an ever longer reach. You can think of it like this. Imagine you are marking distances on a rubber band with a pen. Near one end, you make evenly spaced marks. 1 centimeter, 2 centimeters, 3, and so on. Now start pulling that end, stretching the band. To keep the labels consistent, you have to place new marks closer and closer together in the original material, because the same physical stretch now corresponds to a larger distance on your measuring scheme. If you keep pulling and pulling, the marks leading up to the end of the band crowd together more and more densely. On the band itself, nothing magical has happened. But on your drawn scale, the last bit of material has been inflated into what looks like an enormous interval. The Tortoise Coordinate does something like that to the region near the horizon. Far from the black hole, r star grows almost in lockstep with r. If you move outward by a comfortable number of kilometers, both coordinates increase by nearly the same amount. Space feels ordinary. As you move inward toward the radius associated with twice the mass parameter, r star begins to lag. Each step toward the horizon costs more and more in r star units. In the limit, as r approaches the horizon value, r star runs away toward minus infinity. On the page, the horizon has been pushed infinitely far away along this new ruler. Even though the actual proper distance in spacetime is finite, and the falling astronaut reaches it in finite wristwatch time. This is where the echo of the ancient paradox appears. In one of the classic stories told by the philosopher Zeno, Achilles, the swift runner, chases a tortoise that has a small head start. To reach the tortoise, Achilles must first reach the point where the tortoise began. By then, the tortoise has moved on a little. Achilles must then reach this new point, by which time the tortoise has again moved forward. The sequence of catch-up points becomes a series of ever smaller intervals. At each stage, Achilles closes most of the gap, but never quite all of it. The paradox suggests that motion itself is suspect. How can Achilles ever overtake the tortoise if there are infinitely many points to reach? Of course, in real life, Achilles passes the tortoise easily. The infinite series of steps can be summed. The total time it takes can be finite. The paradox lives in the way you slice the motion, not in the motion itself. The Tortoise Coordinate near a black hole plays a similar trick. It slices the approach to the horizon into an infinite sequence of smaller and smaller coordinate intervals. The astronaut's fall, seen through this lens, looks like Achilles' endless pursuit. Each advance in r star takes them closer. But the horizon itself recedes to an unreachable, infinitely distant point on the scale. Yet from the astronaut's own perspective, and in terms of their proper time, the crossing still happens in a finite interval. The infinite stretch is in the coordinate, not in the physics. Once you see that, the statement, "It takes an infinite time to reach the horizon," starts to lose its authority. You realize it is not a universal truth about black holes. It is a story told by one particular choice of time and distance labels. The story is narrated by the Schwarzschild T and its tortoise companion r star, as interpreted by an observer who lives infinitely far away and never falls in. The disagreement between the outsider and the infaller is now easier to phrase. From the point of view of someone who stays safely far away, using Schwarzschild time as their clock and the Tortoise Coordinate as their ruler, the horizon lies at a tortoise distance of -infinity. Light rays emitted outward from near that surface take longer and longer in t to reach them. The redshift grows without bound. Their equations tell them that the act of crossing is endlessly postponed. They are, in a sense, looking at Achilles' infinite sequence of catch-up points and forgetting that Achilles' own time does not care about that slicing. From the point of view of the astronaut, following their proper time and local measurements, the story is straightforward. They fall. Gravitational tidal forces grow stronger. In a calculable, finite span of their own seconds and minutes, they pass the horizon. Their clocks do not slow or stop in their own frame. They never notice the tortoise coordinate diverging. That divergence is a feature of the observer's chart, not of their body's history. By the time we reach the 1960s, relativists have become comfortable with this sort of subtlety. Coordinate tools like the Tortoise Coordinate are no longer seen as exotic tricks. They become part of the standard kit described in big synthesis texts and research papers. The horizon is treated as a geometric feature, a null surface, where the light cones tip irrevocably inward rather than as a brick wall or an intrinsic singularity. The mathematics of geodesic extension and global structure takes priority over the misleading intuitions of any one coordinate system. For someone watching all of this, translated into popular culture, it can feel as though two different universes are being described. One is the universe your television shows you. An object falling toward a glowing ring, its approach slowing, freezing, smeared into a thin band of light on the brink. Time, you are told, stops at the horizon. The other is the universe the professional relativist describes, where no local clock ever stops at the horizon, and the tortoise coordinate's infinite stretch is recognized as an artifact of the way we have chosen to draw the grid. The discrepancy between these pictures is not because one group is lying. It is because the map they are using has quietly changed. An everyday analogy can help. Imagine you are watching a friend walk away from you down a long corridor, but you are forced to view them through a strange lens that distorts depth. At first, the lens behaves normally. Each step your friend takes appears as a regular movement on your screen. As they approach the far door, the lens begins to warp the image. Distances near the end of the corridor are stretched. Each additional step looks smaller than the last. Your friend seems to slow down, then almost stall, their approach to the doorway stretched out over an absurdly long time in your view. If you trusted only the screen, you might conclude that there is some invisible barrier near the far door. That time is literally slowing for your friend as they approach it. But if you stepped into the corridor yourself, without the lens, you would see them walk at a steady pace, reach the door, and step through. The warped lens is the combination of Schwarzschild time and the tortoise coordinate. The ordinary corridor is the space-time the infaller actually experiences. The door is the horizon. The myth that time stops there is born from mistaking the lens for the world. Tortoise coordinates are useful not because they are somehow more real, but because they reveal the structure of that lens. They show explicitly how the near-horizon region is stretched in the outsider's chart, how the infinite delay is created. Once that is visible, you can separate what belongs to the coordinate story from what belongs to the underlying geometry. This is part of a broader lesson that general relativity delivers, again and again. Statements like, "Nothing ever falls in," or "time stops at the horizon," are not invariant truths. They are declarations made in a specific coordinate language. Change the language, and those sentences can lose their meaning. What survives are the coordinate-independent features, the existence of a null surface that no causal signal can cross outward, the fact that geodesics of certain types can be extended through it, the presence or absence of curvature singularities deeper inside. By the time the tortoise coordinate settles into the literature, the event horizon has largely shed its identity as a material surface. It has become, in the minds of most relativists, a structural feature of spacetime, the boundary of the region from which future-directed null geodesics cannot reach infinity. The language is dry, almost austere, but it is also safer. It does not confuse the stretching of a coordinate with the freezing of reality. For us, as late-night listeners or viewers, there is a quiet payoff. Once we understand that the apparent standstill at the horizon is a coordinate story, we can stop treating it as a metaphysical revelation. The horizon is not where time ends. It is where one particular way of describing time becomes ill-behaved. Our astronaut does not hang forever over the brink. They cross, and their future is swallowed by the interior. The other side of the horizon, in this first precise sense, is the domain of futures that can no longer send whispers back to us. The Tortoise Coordinate, for all its cleverness, is still only a stepping stone. It makes clear how the horizon is stretched to infinite distance in one sense, and how that stretching produces the illusion of an infinite fall. But it does not yet give us a chart that lets light and matter cross the horizon on paper as smoothly as they do in the infaller's frame. For that, we need to go one step further and stop using t as our time altogether. Instead of building our coordinates out of a static outside clock and a stretched radial scale, we can build them out of light itself. We can follow the ingoing and outgoing null rays, define new variables that ride along those paths, and discover a way of drawing the spacetime in which the horizon is just another line, regular and finite, that both geodesics and light rays cross without mathematical drama. Those light-based, or null, coordinates will lead us first to Eddington-Finkelstein charts, where the black hole's one-way nature appears with clean clarity, and then, later on, to the fully extended Kruskal-Szekeres picture, where what looks like beyond the black hole can be drawn on a single finite page. So let us do what our old coordinates refuse to do. Stop measuring time with a distant clock and start measuring it with light itself. If we follow the beams that actually feel the curvature, a different picture of the horizon begins to appear. Light is the strictest creature in relativity. It always moves at the same speed in vacuum. And its paths in spacetime, the null geodesics, are the sharp edges of the light cones that decide what can influence what. If any coordinate system deserves to be taken seriously near an event horizon, it is one that treats those paths with respect. The Schwarzschild chart does not. Near the horizon, the equations that describe radial light rays, written in terms of the Schwarzschild time and the usual radial coordinate, become twisted. Outgoing light seems to crawl. Ingoing light is described in a way that makes the horizon look stranger than it really is. The Tortoise Coordinate, that stretched radial scale we introduced, partly repairs this by making the light paths look simple again. But it still keeps the dysfunctional Schwarzschild time as its clock. The next step is to surrender that time. Arthur Eddington, in the early 1920s, was already exploring coordinate systems that followed light in curved spacetimes, especially in the context of understanding how starlight bends as it passes near the Sunday. He had the intuition that if you are going to draw a faithful map of a relativistic world, you should let beams of light guide your pen. His work did not yet crystallize the idea of a black hole horizon as we understand it today, but it planted the seeds. Decades later, in the year 1958, David Finkelstein picked up those seeds and planted them squarely at the Schwarzschild radius. Instead of asking how to fix the horizon for some arbitrary outside observer, he asked what the spacetime would look like if you chose coordinates built around ingoing light rays themselves. The result is what we now call the ingoing Eddington-Finkelstein coordinates. The idea, stated gently, is this. Keep the usual radial coordinate and the angular coordinates that label directions on the sphere. These are still convenient for saying how far you are from the center and in which direction, but replace the Schwarzschild time with a new time coordinate that flows along with ingoing light. In practice, you take the old time and the Tortoise Coordinate and combine them into a single quantity often called v, the advanced time, where the original Tortoise Coordinate stretched the radial direction. This new combination stretches and shifts the time coordinate along with it. Radial ingoing light rays become simply lines of constant v. They no longer suffer from the strange slowing that plagued them in the Schwarzschild description. When you rewrite the spacetime metric in terms of this new time and the old radial and angular coordinates, something subtle but important happens. The mathematical singularity at the horizon disappears. There is no longer any denominator that goes to zero there. No coefficient blows up. The metric components remain finite and smooth at the Schwarzschild radius. On this new map, the horizon is just another null surface, a place where the light cones tip in a particular way, but not a place where the equations themselves fall apart. Surfaces of constant advanced time now stitch together the exterior region and the interior region seamlessly. If you draw them, they look like smooth slices that pass through the horizon without kinks. Infalling world lines cross these slices without interruption. Ingoing light rays, by construction, glide along them. Outgoing light rays, while not as simple in form, are still well behaved. Nothing in the mathematics insists that motion has to pause at the horizon. The geodesics, both null and time-like, continue. This is the coordinate language that respects what the falling astronaut already knew in their bones, that crossing the horizon is locally uneventful. From the point of view of the distant observer who clings to Schwarzschild time, this does not change the visual story. Their telescope still receives redshifted signals that slow and fade, because that is a statement about the paths of light through curved spacetime and the way frequencies are stretched on their journey outward. The outside clock still records an ever longer delay between successive pulses. But if that observer chooses to describe the geometry using the Eddington-Finkelstein chart, they no longer have to pretend that the astronaut's world line ends at the horizon. They can acknowledge, in their mathematics, that the infaller continues into the interior, even if no signal of that fact ever reaches them. The power of these coordinates lies not just in their regularity, but in their honesty about causality. In the ingoing Eddington-Finkelstein description, the horizon reveals its one-way character, with clean clarity. Ingoing light crosses it freely. Outgoing light, once inside, cannot turn around and escape. The geometry of the metric makes this unavoidable. If you draw the light cones in these coordinates, they tilt in such a way that all future directed null directions at or inside the horizon point inward. The horizon becomes, in this language, exactly what Finkelstein called it: a one-way membrane for causal influence. You can also construct an outgoing version of these coordinates, where instead of advanced time you use a retarded time built from outgoing rays. In that chart, it is the behavior of light coming out of the central region that looks simplest. The geometry, described in that way, resembles a time reverse of the black hole, a white hole, from which things can emerge, but into which nothing can fall. This is a strange but important lesson. The same underlying spacetime can present a black hole character or a white hole character, depending on which family of null coordinates you promote to the role of time. The difference is not arbitrary, because one choice aligns with the actual arrow of time in our universe, the direction in which entropy increases and collapse occurs. But it shows that when we ask about the other side of a horizon, we are smuggling in assumptions about the direction in which we are reading time itself. In the real astrophysical world, matter collapses. Stars burn their fuel, lose pressure support, and in some cases fall inward under their own gravity, until a horizon forms. There is no phase in that story where a pristine white hole explodes outward, ejecting matter that then miraculously reassembles into coherent structures. The arrow of time points toward increasing entropy. The collapsing configurations that form black holes are overwhelmingly more likely than any hypothetical time-reversed counterparts. Eddington-Finkelstein coordinates, especially the ingoing version, fit this narrative. They align naturally with the physics of material and radiation streams falling across a forming horizon. In numerical simulations of collapse, in analytic models of infall, in conceptual pictures of accretion, it is these null-based charts that make the behavior of the system transparent. They also prepared the ground for one of the most profound developments in the study of spacetime, the singularity theorems of Roger Penrose. In the mid-1960s, Penrose used methods that lean heavily on null geodesics and causal structure to prove that, under fairly general conditions, Gravitational collapse inevitably produces singular regions where the space-time description breaks down. Instead of focusing on any particular coordinate expression of the metric, he followed the structure of light cones and trapped surfaces. His work showed that once a horizon forms around sufficiently dense matter, the inward tipping of the light cones and the focusing of geodesics are not quirks of Schwarzschild's idealized sphere, but robust features of gravity itself. The causal diagrams that grew out of this work compress infinite regions of spacetime into finite pictures while preserving the light cone structure. They are, in spirit, an extension of the logic behind Eddington-Finkelstein coordinates. Draw your map so that light always travels along lines at 45 degrees, and let the shape of these lines tell you what the universe allows and forbids. All of this may sound far from the original, almost childlike question: what is on the other side of a black hole? But notice how the answer has silently shifted. The other side that these tools make visible is not another place in the ordinary sense. It is a region of spacetime that exists in the same manifold as the exterior, stitched together by smooth slices of advanced time, where future-directed paths all flow toward a singular fate. It is inaccessible to signals that must move outward, but it is part of the same geometric whole. The existence of that region is not a speculation. It is a requirement of the classical theory once certain conditions are met. This other side is also not something that a distant bystander can ever literally see. Their view is limited by the way outgoing light rays emerge from the near-horizon region. The last glimpses they receive of any infaller are those stretched, red-shifted images hovering close to the edge. The rest of the story is private to the object that falls. In a quiet way, this is emotionally charged. We are used to thinking of reality as something that, at least in principle, could be observed by someone, somewhere, if only they had the right instruments. The idea that there exists a region of spacetime whose events are forever inaccessible to the outside, not just practically but in principle, can feel like an affront to that intuition. Eddington-Finkelstein coordinates do not soften that blow. They sharpen it. They tell you that the infaller's world line continues, that the interior events are there in the geometry, and that no trick of observation will ever let you reconstruct them from the outside. The other side of the horizon, in this sense, is a difference of experience. It is the part of the story that belongs only to objects that have committed to crossing. No external record, no archive of photons, no distant telescope will hold the full account. Seen from the perspective of the infaller, the new coordinates are almost reassuring. They validate what their own clock and instruments would tell them. There is no infinite delay. No drama at the crossing. The horizon is simply passed. From that moment on, however, the structure of their future is constrained by the geometry in a way that no change of coordinates can undo. For the outside observer, the Eddington-Finkelstein chart is a reminder of humility. It says, your coordinates are a convenient language, not the universe itself. They can hide continuity where there is none, and they can invent discontinuity where none exists. If you insist on describing everything in terms of Schwarzschild time, you will be forced into awkward statements about things freezing forever at the edge of nothingness. If you allow yourself to switch to a null-based time, you recover a calmer, more coherent narrative. At this point in the journey, we have a set of tools that let us draw the black hole, interior and exterior, as one connected spacetime, at least for the simple, non-rotating case. We have coordinates that cross the horizon smoothly. We have causal diagrams that show how light cones tip and geodesics focus. We have a clearer idea of what kind of other side is already encoded in the classical theory, without invoking exotic matter or speculative quantum effect. And yet, there is a sense that we are still looking at only part of the picture. The Schwarzschild solution, as originally written, is a local description. It covers a region outside the horizon and hints at the interior. Eddington-Finkelstein coordinates extend that region and make the horizon regular, but they do not yet reveal the maximal spacetime that the equations allow. There may be parts of the manifold that these charts do not show, in the same way that a single patch of a globe does not display the entire Earth. If we are brave enough to insist that every geodesic that can be extended should be extended, and that our coordinates should cover all of those extensions without artificial edges, we are led to an even bolder map. A map in which the black hole region is only one piece in a larger diagram that includes a white hole region and even another exterior that looks, on paper, like a separate universe. To see that map, and to understand why it tempts so many people to talk about other sides in a more literal sense, we have to let go of our current coordinates once more and move to a system where the entire Schwarzschild spacetime can be drawn on a single finite page. Imagine holding that page in your hands for a moment, seeing an entire universe flattened into a single, quiet drawing. At first, it looks almost too simple, as if the drama of a black hole had been reduced to a few straight lines and a pair of crossing diagonals. The road to that drawing begins with a question that has nothing to do with drama and everything to do with completeness. Once Einstein's equations have given you a spacetime, how far are you allowed to push it? How much of that spacetime are you truly seeing when you stick to one convenient coordinate chart, like Schwarzschild or Eddington-Finkelstein? Are there regions those charts simply fail to show, not because the physics ends, but because the coordinates run out? In the late 1950s, two physicists, Martin Kruskal and Kosmology, took those questions seriously for the Schwarzschild solution. Instead of treating the familiar form of the metric as the whole story, they asked, what is the maximal analytic extension of this space-time? In plainer language, if you insist on extending every geodesic as far as the equations will allow, without hitting artificial coordinate edges, what full manifold emerges? To answer that, they needed yet another set of coordinates. Not the original Schwarzschild time and radius, which break at the horizon. Not even the more forgiving Eddington-Finkelstein chart, which crosses the horizon but still favors one direction of light over the other. They needed a system in which both ingoing and outgoing light rays look as simple as they do in flat spacetime, and in which the horizon is not a special point of failure, but just another null surface. The construction, in its technical details, is intricate, but its spirit is straightforward. You begin with the null coordinates that lie behind the Eddington-Finkelstein descriptions. An advanced time built from ingoing rays, and a retarded time built from outgoing rays. Then you combine them into two new coordinates, often called something like a pair of symmetric null variables. These new variables are chosen so that the metric becomes regular at the horizon and so that light rays trace lines at 45 degrees, just as they do on the simple spacetime diagrams of special relativity. When the dust settles, you have what we now call Kruskal-Szekeres coordinates. In this chart, the Schwarzschild metric takes on a new form. The complicated factors that blew up at the horizon have disappeared. The event horizons themselves appear as straight diagonal lines. Radial light rays move along lines tilted at 45 degrees, one family going inward, another outward. The singular region, where the curvature truly does diverge in the classical theory, lies not at the horizon but deeper inside, drawn as a space-like boundary. If you sketch this spacetime in the plane of the two Kruskal-Szekeres null coordinates, with angles chosen so that light always follows those diagonal lines, an unexpected structure appears. What had seemed, in the original Schwarzschild chart, to be a single exterior region and a single interior, turns out to be only one part of a larger, four-fold pattern. Relativists often label these parts as four regions. To keep the language soft, let us speak of them as Region 1, Region 2, Region 3, and Region 4. Region 1 is the piece we are most familiar with. It is the external universe outside the black hole. The place where the radial coordinate r exceeds the Schwarzschild radius, where an observer can in principle remain forever far away, sending and receiving signals over arbitrarily long times. In the Kruskal-Szekeres plane, this region occupies one wedge of the drawing, bounded on one side by an ingoing horizon and on another by an outgoing horizon. Region 2 lies below Region 1 in the diagram. It is the black hole interior. In this region, the radial coordinate has fallen below the horizon value, and the future of every time-like geodesic is pulled inevitably toward the central singularity. In the Kruskal picture, That singularity is drawn as a horizontal line, a space-like boundary that all future directed paths in the interior eventually intersect. This region is the mathematical home of the fate we described earlier. Once you cross the horizon, all your possible futures end at the singularity in finite proper time. Region 3 sits above Region 1. It is the time reverse of the black hole interior, the white hole region. Here, the singularity lies in the past, drawn as a space-like line from which geodesics and light rays emerge, moving outward toward the horizons. Nothing can enter this region from the outside. It is a domain from which matter and light can only escape. If you trace ingoing light rays backward in this region, they do not converge on some collapsing star surface. They originate from the white hole singularity itself. Region 4 mirrors Region 1 across the central vertical axis of the Kruskal diagram. It is a second exterior region, asymptotically flat and structurally very similar to our own. Observers living there see a black hole in their sky, with its own horizon and interior. Yet, in the drawing, their region is connected to ours through the shared interior and the white hole past. In many popular accounts, this is what is meant by the other universe on the other side of a black hole. The first time you see this four-region diagram, it can feel like an enormous revelation. A single Schwarzschild solution, once extended to its maximal analytic form, seems to contain not only our universe outside a black hole and its interior, but also a white hole and a second universe beyond. Light and geodesics weave between these regions in a pattern that is hidden in the original Schwarzschild coordinates. The more you stare at the picture, the more it resembles some kind of cosmic transit system, with the black hole and white hole acting as hubs between two external worlds. It is no wonder that, as these ideas filtered into popular science books in the 1970s and 1980s, the image of a black hole as a bridge to another universe became almost irresistible. Diagrams showing the Kruskal-Szekeres spacetime, sometimes simplified and redrawn, appeared alongside imaginative narratives about travelers falling into a black hole in our universe and emerging into some distant elsewhere, perhaps a whole new cosmos. But the Kruskal diagram, for all its elegance, is not telling you that such journeys are possible. It is telling you that, in the maximal analytic extension of the eternal Schwarzschild solution, the four regions are joined in a particular geometric way. The existence of Region 4 in that extension is a mathematical statement about how geodesics can be continued if you refuse to cut them off artificially at coordinate boundaries. It is not, by itself, a promise that any physical process in our universe can carry a spacecraft from Region 1 to Region 4. If you examine the causal structure more carefully, the limitations become clear. Consider an observer in Region 1, outside the black hole. If they remain at a safe distance, their world line stays entirely within that region. They may see light signals from the vicinity of the horizon, but they never cross it. If they decide to fall inward, following a time-like geodesic or even firing their rockets to hasten the descent, their path takes them from Region 1 into Region 2. Once inside Region 2, every future directed time-like path heads toward the singularity. There is no route that carries them back out to Region 1, and there is no time-like geodesic that exits into Region 4. To reach Region 4, along a path that stays within the future light cone at every point, would require a trajectory that somehow bends around the singularity without ever hitting it, crossing from one exterior to the other. The Kruskal-Szekeres structure does not allow such a path. Attempts to imagine travel from our universe to the other exterior via the black hole are forced into non-causal routes, trajectories that would have to move faster than light or violate the basic causal ordering of events. The connection between Region 1 and Region 4 is real in a geometric sense. They are part of the same extended manifold. But the door between them is not open to causal travelers. The white hole region adds another layer of subtlety. In the Kruskal picture, the past singularity of Region 3 feeds both external regions. Light rays and geodesics can emerge from the white hole interior into either exterior. If you trace certain paths backward, you find they originate not in the smooth past of an ordinary universe, but on that singular line. This is mathematically consistent within the extended Schwarzschild solution, but it is physically unsettling. Where did that white hole come from? What process, consistent with our thermodynamic arrow of time, could produce a space-like singularity in the past that ejects matter and radiation in such a perfectly coordinated way? No known mechanism in realistic cosmology or stellar evolution gives rise to such a structure. The white hole in the Kruskal diagram is, in that sense, a formal ghost of time reversal, a piece of the maximal extension that does not correspond to anything we expect nature to actually realize. Here, the geometric analogy becomes useful. Imagine you are given a map that shows only the northern hemisphere of Earth, cut off sharply at the equator. From the perspective of someone who has never seen a globe, it might be tempting to think that the planet ends there. If you insist on completeness, however, you realize that there must be more. The geometry of a sphere demands a southern hemisphere as well, joined smoothly along the equator. To get the full picture, you add that missing half and glue it on. You now have a more complete manifold, a surface without edges. Kruskal-Szekeres coordinates do something similar for the Schwarzschild solution. The original chart covers only part of the spacetime, cutting off certain geodesics at the horizon. The maximal extension adds the missing parts, so that every possible geodesic either continues indefinitely or ends at a true singularity, not at a coordinate artifact. Region 4 and the white hole region emerge from that insistence on completion. The way the southern hemisphere emerges from insisting that a sphere have no boundary, but there is an important difference between the globe analogy and the black hole space-time. On Earth, we can walk from the northern hemisphere into the southern one. The equator is not a barrier, only a line of latitude. In the Kruskal diagram, the analog of the equator is not the horizon but something more abstract. The requirement that the mathematical extension be analytic, that the metric be as smooth as possible wherever curvature remains finite. The horizons in that picture are not like the equator. They are one-way causal boundaries. And the white hole singularity that appears as a past boundary is more like a tear in the manifold than a smooth cap. This is where Penrose diagrams enter the story. In the 1960s, Roger Penrose and others developed a technique called conformal compactification. The idea is to rescale the metric in such a way that points at infinity are brought to a finite distance on the page while preserving the causal structure the way light cones tilt and intersect. When you apply this method to the Kruskal-Szekeres spacetime, you can draw the entire extended Schwarzschild universe in a single finite diagram, often shaped like a diamond. In that diamond, the top point represents future null infinity, the place where outgoing light rays eventually end up. The bottom point represents past null infinity, where incoming rays originate. The left and right corners represent spatial infinity in the two exterior regions. The event horizons appear as straight diagonal lines slanting inward from the sides toward the center. The black hole singularity is a horizontal line near the top. The white hole singularity is a horizontal line near the bottom. Light rays always travel along lines at 45 degrees in this picture. You can see at a glance which events can influence which others, which world lines are trapped inside the black hole, and which remain forever outside. The four regions stand out clearly. Two external diamonds on the left and right, a black hole interior at the top center, and a white hole interior at the bottom center. Looking at such a Penrose diagram, it is hard not to feel that you are seeing the whole truth about the Schwarzschild spacetime. Every infinity has been tamed into a finite edge. Every horizon is a neat, straight line. The casual eye is drawn to the symmetry between the two exterior regions and between the black hole and white hole interiors. The temptation is to say, this is what a black hole really is, a gate to another universe with a mirrored structure in time. But the Penrose diagram, like any map, is a distilled representation. It encodes certain aspects of the geometry very faithfully, especially the causal relationships, but it also leaves out others. It does not tell you how the spacetime was formed. It does not show you collapsing matter or the fact that, in a realistic collapse, there is no past white hole singularity. It represents an eternal black hole that has always existed, unchanging, with its full four-region structure in place from the infinite past to the infinite future. That eternal idealization is a powerful mathematical object. It is also, most likely, not realized in our universe. Real black holes form from the gravitational collapse of matter. If you draw a Penrose diagram for such a collapse, you do not see the white hole region and the second exterior universe. In their place, you find a region describing the infalling matter and a past that looks much more like ordinary space-time. The future black hole singularity remains. Penrose's theorems tell us that under broad conditions, it must, but the mirrored past singularity and the other exterior are absent. In that more realistic picture, there is only one exterior universe. The horizon forms at a finite time, as seen by outside observers. The black hole interior opens up in the future of the collapsing star. There is no pre-existing eternal bridge to another world. The other side, suggested by region 4 in the Kruskal diagram, is replaced by the much more modest, but physically grounded other side we have already discussed. The interior region of no return, whose events are permanently hidden from the outside. So where does this leave us? On the one hand, Kruskal-Szekeres coordinates and the associated Penrose diagrams reveal something profound. They show that general relativity, when taken at face value in its simplest vacuum solution, naturally contains structures that look like white holes and parallel exteriors. They demonstrate that horizons are not places where the mathematics stops, but surfaces that can be crossed in extended charts. They sharpen our understanding of what inside and outside mean in a world where space-time is curved. On the other hand, they also serve as a caution. The enticing regions that appear in the maximal extension are not guaranteed to be realized in nature. They are the shadows cast when we push an idealized solution, a perfectly symmetric, eternal, vacuum black hole to its mathematical limits. When we reinstate the messy, asymmetric, evolving matter content of the real universe, many of those shadows evaporate. The white hole region and the second exterior universe are, in this sense, ghosts of the equations. They live naturally in the realm of perhaps, possible in the abstract, constrained or erased by the actual history and boundary conditions of our cosmos. And so the question that hangs over the Kruskal diagram is quietly the same question that hangs over our entire search for the other side of a black hole. Are these extra regions, these white hole interiors and parallel exteriors, physically real places that have existed or could exist in some corner of reality? Or are they the artifacts of a mathematical completion, beautiful and suggestive, but forever uninhabited by matter, never woven into the lived history of any universe at all? The most delicate of those ghosts is the one that runs time backwards. If a black hole is a promise that nothing ever comes out, a white hole is the opposite promise. Nothing ever gets in. That is the simplest way to define it. A black hole is a region of space-time from which no future directed causal path escapes to infinity. A white hole is a region into which no such path can enter from outside. In one case, everything falls in and nothing returns. In the other, everything must come out and nothing is allowed to fall back. If you like images, you can picture a white hole as a one-way fountain in the fabric of space-time itself, constantly shedding whatever it contains, yet forever sealed against any new arrivals. In the maximal extension of the Schwarzschild solution, that fountain is drawn quite explicitly. In the Kruskal-Szekeres diagram, the white hole interior sits above the past and below the event horizons, occupying the region where the singularity is a line in the past instead of the future. Light rays emanate from that singular line and travel outward toward the horizons. Time-like world lines that live in that region trace back to the singularity if you follow them into the past. There is no way, within the classical theory, to extend those world lines further back before that singular boundary. The white hole is, in that sense, a place where histories begin, not where they end. The behavior of light there is as striking as in the black hole interior, just in the opposite temporal direction. In the black hole region, every future directed light cone tilts inward. Every allowed future leads toward the singularity. In the white hole region, every past directed light cone tilts inward. Every allowed past leads back to the singularity. Nothing can fall into the white hole. because any attempt to define a path that begins outside and enters would require you to violate the light cone structure. It would require a jump that moves faster than light or breaks the causal ordering of events. On paper, this makes perfect sense. The equations allow it. The Kruskal-Szekeres coordinates describe it cleanly. The Penrose diagram compresses the whole story onto a finite diamond, where the white hole singularity sits as a neat horizontal line in the lower interior. For a mathematician asking only what shapes the equations admit, a white hole is as acceptable a feature as a black hole. For a physicist thinking about real stars and real time, it feels different. In the mid-1960s, Roger Penrose proved a series of singularity theorems that changed how we think about gravitational collapse. Using the language of null geodesics and trapped surfaces, he showed that, under quite general conditions, a region of spacetime in which light is so strongly focused that it cannot escape will inevitably contain a future singularity. In more intuitive terms, once enough mass falls into a small enough region and an event horizon forms, general relativity predicts that the interior must end in some kind of singular behavior in the future of that collapse. These results gave a rigorous backbone to the idea of the black hole singularity. They tell us that if our understanding of gravity is roughly right and certain energy conditions hold, singular regions in the future are not exotic add-ons, but natural consequences of collapse. They arise at the end of a story in which matter starts in a relatively smooth configuration, evolves under the pull of gravity, and is crushed by its own attraction. There is no analogous story that naturally gives you a white hole singularity in the past. To get the white hole in the Kruskal diagram, you do not begin with an expanding cloud of matter and run it forward in time. You begin with the eternal Schwarzschild solution, which describes a vacuum spacetime with a black hole and white hole already present. And then you ask, what is the maximal analytic extension of this geometry? The white hole appears as part of that extension, a past boundary that you must include if you insist that every geodesic be extendable as far as the equations allow. It is a completion of the map, not the result of any plausible dynamical process. If you try to imagine a physical mechanism that would produce a white hole, you run into trouble almost immediately. You would need matter and radiation to emerge from a singular past surface in such an organized way that they form an event horizon and then flow outward into two external regions. You would need, in effect, a cosmic explosion that is the perfect time reverse of gravitational collapse, with entropy decreasing instead of increasing. The second law of thermodynamics, the rule that entropy in a closed system tends to grow, makes that scenario fantastically unlikely. The universe we observe has a strong arrow of time. Stars form from diffuse gas, burn their nuclear fuel, and move toward more disordered states. Black holes, as far as we can tell, grow by accreting matter and by merging with each other. They are, in a sense, entropy engines. Their presence increases the number of ways microscopic degrees of freedom can be arranged. A perfect white hole would demand the opposite behavior. It would be like watching a cloud of gas in a box spontaneously assemble itself into a cold, dense clump in one corner, while the rest of the box empties out in a coordinated way. The laws of physics do not forbid that entirely, but they assign it an absurdly small probability. Even before Penrose's theorems, this asymmetry between collapse and explosion showed up in simple models. In the year 1939, J. Robert Oppenheimer and Hartland Snyder published a pioneering model of gravitational collapse. They considered a sphere of idealized dust collapsing under its own gravity in the framework of general relativity. Outside the collapsing matter, the spacetime is described by the Schwarzschild solution. Inside, the dust follows a contracting version of a homogeneous cosmological solution. As the collapse proceeds, an event horizon forms, and the interior evolves toward a singular state in a finite, proper time. In that model, there is no white hole in the past. The spacetime begins in a smooth, expanding configuration and ends in the collapsing region at a singularity. The exterior looks like Schwarzschild only after the collapse has progressed enough to form a horizon. There is no pre-existing white hole feeding matter outward. The singularity is future-directed, arising naturally from the dynamics of matter and gravity. This contrast is important. It shows that you do not need a white hole to make a black hole. You can have a black hole form from collapse in an otherwise regular spacetime, with no mirrored past singularity. The white hole of the maximal Schwarzschild extension, with its ghostly past singular line, is therefore not required by physical formation scenarios. It is required by a different demand, that the eternal vacuum Schwarzschild solution be analytically complete. Thermodynamics adds weight to this skepticism. The second law does more than state a statistical tendency. It shapes our expectations about what kinds of macroscopic structures we are likely to see. A black hole fits neatly into that picture. When matter falls in, the horizon area increases. And in modern formulations of black hole thermodynamics, that area is associated with entropy. The black hole acts like an absorber, swallowing chaotic configurations and hiding their detailed microstates behind a few coarse macroscopic parameters. A white hole, by contrast, would look like a device that takes a low entropy state, the neat, compact singularity, and converts it into a high entropy mix of outgoing matter and radiation, but in a way that appears finely tuned when traced backward. Interpreted in reverse, the spontaneous convergence of all those outgoing particles back into a singular line would look like an enormous decrease in entropy, a violation of the natural arrow of time. The only way to make that plausible is to imagine an extremely special boundary condition imposed from the outset, a universe born with a white hole already in place. Physics does not usually work by positing special, unexplained initial conditions in one corner of spacetime. And yet, despite these theoretical reservations, white holes flourish in culture. They show up in science fiction as gateways, as convenient exits to balance the terrifying mouths of black holes. They appear in thought experiments where matter falling into a black hole in one universe emerges from a white hole in another. They populate diagrams in popular books, often drawn as the mirror image of black holes, with arrows of motion reversed. They appeal to a deep narrative instinct. If there is a door that only lets you in, surely there must be a door that only lets you out. Part of this appeal comes from the way white holes map onto an old mythological pattern. Many stories, long before relativity, imagined a symmetrical cosmos. For every descent, there is an ascent. For every underworld, an overworld. For every sink, a source. To have only black holes, only places where matter goes in and does not return, can feel emotionally lopsided. White holes offer a kind of symbolic correction, even if the equations themselves are indifferent to such balancing. The role they play in the mathematics is quieter. In the maximal Kruskal-Szekeres extension of Schwarzschild, the white hole is not a door we choose to install. It is part of making the spacetime geodesically complete. If you take seriously the requirement that every geodesic should either extend indefinitely or end at a genuine singularity, and you start from an eternal Schwarzschild geometry, the white hole region appears as the natural past domain of dependence for certain world lines. It is where those world lines must come from if they are to be extended, given the symmetries and vacuum character of the solution. Seen that way, the white hole is a kind of bookkeeping device for the equations. It ensures that the mathematical structure hangs together neatly. It tells you that, in this idealized eternal spacetime, some paths do not originate in a smooth, low curvature past, but at a singularity. That is a legitimate statement about the geometry. It is not, by itself, an argument that such a region exists in our universe. So when we ask, with our original question in mind, what lies on the other side of a black hole, can we honestly point to the white hole region of the Kruskal diagram and say, there, that is the answer? If we are being faithful to what we know about astrophysics and thermodynamics, the answer has to be cautious. The white hole region is a mathematically consistent part of an eternal vacuum solution. It does not have a known formation mechanism in realistic cosmological or stellar scenarios. It would represent a massive, finely tuned violation of the usual entropy gradient. We have no observational evidence for such objects. They are not strictly forbidden by general relativity, but they are treated by most working physicists as curiosities, not as entities expected to populate the universe. They remain, for now, more like reflections on the far side of a mirror than like destinations. That does not make them meaningless. Thinking carefully about white holes sharpens our understanding of why black holes, with their future singularities, are physically plausible, while their time-reversed cousins are not. It highlights the role of the arrow of time in shaping what kinds of space-time regions we expect to actually see. It reminds us that the full mathematical space of solutions is larger than the subset realized by nature, and that not every feature in an extended diagram corresponds to a real object in the sky. It also nudges us toward other, more tempting structures, where the idea of the other side feels less ghostly and more like a place. In the mid-1930s, Albert Einstein and Einstein-Rosen explored another way that general relativity's equations might connect different regions of space-time. Instead of focusing on singularities in the past or the future, they considered a construction in which two exterior regions are joined by a kind of geometric bridge. What would happen if, rather than inventing a time-reversed fountain, you simply folded space-time so that two distant mouths touched? To talk about an other side that feels less like an abstract ghost of time reversal and more like a tangible where we have to walk out onto that bridge, the structure that later writers, with a touch of imagination, began to call a wormhole. If you try to stand on that bridge, though, the first surprise is how quickly it dissolves beneath your feet. The second is quieter, realizing that geometry can draw a connection that no actual traveler can ever use. In the middle of the 1930s, Albert Einstein was already uneasy with what his own equations seemed to be allowing. The Schwarzschild solution, as people had come to understand it by then, contained something disconcerting. A region where the coordinate expressions misbehaved, and deeper in, a place where the curvature appeared to blow up altogether. To Einstein, who still hoped that general relativity might offer a complete description of particles as smooth fields, the idea of singularities felt like a failure, not a feature. In June 1935, together with his collaborator Einstein-Rosen, he published a paper with a different question in mind. Could one take the Schwarzschild geometry and reinterpret it in such a way that the central singularity was replaced by a kind of bridge? Instead of imagining a point mass sitting at the center of space, perhaps one could imagine two sheets of space-time joined along a throat. The object we call a particle might then be tied to this geometric structure rather than to an ill-behaved point. If you strip away the technical language, the picture is surprisingly simple to visualize. Imagine two infinite, flat sheets of paper, each representing an exterior region of space around a mass. On each sheet, far from the center, the gravitational field is weak, and the geometry looks almost like that of ordinary flat space. Now, cut a circular hole in the middle of each sheet and connect the two holes with a short tube made of flexible material. You have built a crude model of what later came to be called an Einstein-Rosen bridge, a narrow throat linking two exteriors, with the geometry bending inward around the opening on each side. From far away on either sheet, the presence of the bridge is felt as a gravitational field. Test particles fall toward the center, orbit, or escape, much as they would in the usual Schwarzschild description. But if you take a slice of the geometry at a fixed moment of time, the spatial section no longer looks like a single sheet with a puncture. It looks like two sheets joined by that neck. Each side has its own asymptotically flat region, its own notion of far away. The throat is the place where the two meet. In the language of the Kruskal-Szekeres extension, this construction corresponds to the way constant time slices stretch across from region 1, our exterior, through the interior geometry, and back out into region 4, the second exterior. The Einstein-Rosen bridge is, in that sense, the most direct expression of the connection between those two external worlds. It is the structural other side, built into the mathematics. Seen only in a diagram of space, it is almost irresistible to think of it as a tunnel. You picture spacecraft entering the mouth in our region, traversing the narrow tube, and emerging in the other exterior. You imagine messages, particles, even whole civilizations using the bridge as a shortcut. The idea of the wormhole as a traversable portal almost writes itself. Later popular culture, and even some speculative physics, would lean hard into that image. But the original Einstein-Rosen bridge, as it lives in classical general relativity, is not a traversable tunnel. It is a momentary structure on a slice of time, one that pinches off too quickly for any time-like path to get through. The key lies in remembering that space-time is not just space plus time, glued together in a static way. The shape of space can change as time flows, and those changes can be so extreme that they cut off routes that looked open in a frozen picture. When you analyze the full four-dimensional geometry of the Schwarzschild solution, you find that the bridge between region 1 and region 4 exists only as an instantaneous feature in a particular slicing. In the actual dynamical story of the space-time, the throat contracts and closes faster than any physical traveler can traverse it without leaving the realm of allowed causal motion. If you start from region 1 and fall inward, your world line carries you into region 2, the black hole interior. The curvature grows. In finite proper time, you intersect the future singularity. There is no choice of initial velocity, no cunning combination of rocket burns that will send you through the throat and back out into region 4 while keeping your path timelike and future-directed. The bridge is there in the geometry, but it is not a bridge you can walk across. You can see this more concretely if you look again at the Penrose diagram of the extended Schwarzschild spacetime. The Einstein-Rosen bridge appears in the way certain spatial slices cut across the diamond, linking the two outer regions through the inner structure. But every future-directed time-like path that begins in our exterior and crosses the horizon ends at the singularity, not in the other exterior. Paths that would connect the two exteriors directly while staying within the allowed light cones simply do not exist. Even light cannot cheat this fate. Null geodesics that start in region 1 and cross into region 2 cannot veer around the singularity and emerge in region 4. To do so would require them to bend in ways the curvature does not permit. The geometry whispers connection in the sense of shared structure, not in the sense of practical passage. And the situation becomes even more unforgiving when you move away from the exact, symmetric, eternal Schwarzschild idealization. The Einstein-Rosen bridge is a fragile creature. It relies on the precise vacuum structure of the extended Schwarzschild solution and on a carefully chosen notion of time slicing. Introduce even small perturbations, additional matter fields, radiation, rotation, asymmetries, and the delicate balance that allows the neck to exist as drawn is upset. In many analyses, the throat either collapses rapidly into a more conventional black hole interior or fails to form in the first place. Later work on wormholes in general relativity, especially in the late 20th century, made this fragility even more explicit. To support a static, traversable wormhole throat, one typically finds that the stress-energy tensor must violate certain energy conditions that are normally taken as reasonable assumptions about ordinary matter. In more intuitive terms, you need something that behaves like matter, with negative energy density along some paths. A form of exotic matter that can hold the throat open against the tendency of gravity to pinch it off. On microscopic scales, quantum field theory does allow transient regions where energy densities dip below what classical intuition would allow, as in the famous Casimir effect. But there is no known macroscopic source of the kind of sustained negative energy distribution that a stable wormhole throat would require. Without such a support, the Einstein-Rosen bridge in Schwarzschild is not a corridor. It is more like a fleeting fold in the fabric, present in a mathematical snapshot, gone before any traveler can cross. This has not stopped wormholes from becoming some of the most beloved devices in science fiction. In the film Interstellar, for example, which premiered in late October of the year 2014, the central plot device is a large, stable wormhole placed near Saturn, providing access to distant regions of the universe. The visual effects team, advised by physicist Kip Thorne, went to great lengths to render this wormhole in a way that respected many features of general relativity. Viewers see distant galaxies distorted and lensed around a spherical portal. The idea that such a wormhole could be kept open by exotic matter is mentioned in passing, but the deeper compromises are left off-screen. The wormhole in that story is not the Einstein-Rosen bridge of an eternal Schwarzschild black hole. It is an imaginative leap beyond it, a wormhole that has been engineered, stabilized, and placed for narrative convenience. That does not make it scientifically meaningless. Thought experiments of this kind can be useful in probing what relativity would and would not allow, given some hypothetical matter content. But it is worth keeping in mind that the classical bridge Einstein and Rosen studied was already a sign of how tightly the universe limits our desire for shortcuts. There is a further twist that belongs to a newer frontier, one that we will only touch lightly. In the early 21st century, some theoretical physicists began exploring a conjecture that ties together two seemingly different ideas: Einstein-Rosen bridges and quantum entanglement. The slogan, often spoken as ER is EPR, suggests that the geometric connections represented by wormhole-like structures may be deeply related to the non-local correlations of entangled quantum states first discussed in the famous Einstein-Podolsky-Rosen argument. This conjecture lives in the realm of quantum gravity and holography, far beyond the classical Schwarzschild solution. In that speculative landscape, wormhole-like geometries can appear as dual descriptions of entangled quantum systems, and the question of traversability becomes tangled with the structure of quantum information. For our purposes, it serves mainly as a reminder that even the simple picture of an Einstein-Rosen bridge may acquire new layers of meaning when you move beyond classical general relativity. But none of these developments, classical or quantum, erase the basic lesson that the original bridge taught. A connection can exist in the geometry without offering a physically usable path. The other side can be there in the extended map and yet be forever beyond the reach of any causal traveler. The space of solutions admitted by the equations is richer than the space of journeys that respect the speed of light and the arrow of time. The universe is not obligated to turn every geometric possibility into a navigable route. In the context of our guiding question, this matters. If someone points to the Einstein-Rosen bridge as the answer to what lies on the other side of a black hole, the honest response is split. Yes, in the maximally extended Schwarzschild solution, there is another exterior region geometrically connected through a bridge-like structure. No, in that same solution, there is no way for an infalling observer from our universe to pass through the throat and emerge there. The other universe is more like a neighboring room whose door is painted on the wall, a consequence of how the manifold is completed rather than a promise of travel. Up to this point, we have also been playing a particular game. We have treated the black hole as eternal, a structure that exists for all time, with its horizons and interiors and bridges fully formed in the infinite past and persisting into the infinite future. That is what the pure Schwarzschild solution describes. It is an immensely useful toy model. It lets us study the causal structure and the behavior of geodesics in a clean setting. It is also, almost certainly, an idealization that no real object in the universe exactly matches. Real black holes are not eternal geometries written in the vacuum of the equations. They are born. They form from collapsing stars, from dense clusters, perhaps from the mergers of earlier black holes. They grow by accreting matter and swallowing radiation. They emit feeble Hawking radiation over inconceivably long timescales. Their horizons switch on at finite moments in the history of the universe. They are embedded in a cosmos that began in a hot, dense state and has been expanding and cooling ever since. The moment you include that birth and that surrounding history, the neat four-region structure of the eternal Schwarzschild spacetime changes. The white hole past disappears. The second exterior region never appears. The Einstein-Rosen bridge, as drawn in the maximal extension, is replaced by a more modest story. One exterior universe, one black hole interior, and a horizon that forms and grows as matter falls in. And with that change, many of the most dramatic other sides that the pure geometry seemed to offer turn out to belong not to the universe we live in, but to the shadows cast by an idealization. The equations can stretch a bridge between universes on paper, but the sky keeps answering with something else. Stories that begin, burn, and end. If we listen to those stories carefully, a different kind of other side comes into focus. The first serious attempt to tell that story with general relativity came in the late 1930s, long before the word black hole existed. In the year 1939, Robert Oppenheimer and Hartland Snyder asked a simple, brutal question. What happens if you take a massive star, strip it of all the messy complications, and just let gravity do its work? They imagined a sphere of idealized dust, no pressure, no radiation, just matter, initially spread out in a smooth way, beginning to fall inward under its own gravity. Inside this sphere, space-time looks a bit like a closed, contracting universe. Outside, where there is no matter, the geometry is exactly Schwarzschild. The star has a surface, a physical boundary where the interior solution matches onto the exterior vacuum. As the collapse proceeds, that surface shrinks. The density rises. At a certain point, something quiet but dramatic happens. The surface falls inside its own Schwarzschild radius. An event horizon forms, not as a pre-existing feature of an eternal geometry, but as a moment in the life of a star. From then on, any light emitted just outside the surface has a harder and harder time escaping. Light emitted just inside the horizon can never escape at all. Inside the collapsing dust, the story continues. The matter keeps falling. In finite proper time, according to the clocks carried by the dust particles, the entire mass is crushed into a region of arbitrarily large curvature. In the language of the theory, a singularity forms in the future of the collapse. You will notice what is missing from this tale. There is no white hole in the past. The space-time begins in a relatively ordinary state, a star at finite density, sitting in an asymptotically flat universe. There is no past singularity from which matter explodes outward. The exterior region is not an eternal black hole that has always existed. It is a region that gradually comes to resemble Schwarzschild outside the collapsing star. The event horizon is not something you draw once and for all on a Penrose diagram and then label given. It is something that forms. If you were to draw a causal diagram for this collapse, compressing infinities as Penrose taught us to do, it would look different from the eternal Kruskal diamond. The upper part, the black hole interior and its future singularity, would still be there. The horizon would still appear as a diagonal line, the boundary of no return. But the lower part, where the white hole and the second exterior region used to live, would be replaced by a region filled with collapsing matter, and by an ordinary past that traces back to whatever cosmic history you choose to plug in, perhaps. In a larger setting, the hot early universe we infer from cosmology. Outgoing light rays in this new diagram do not begin their lives on a pristine past singularity. If you follow them backward, they come from the body of the collapsing star, or from the wider universe beyond, and ultimately from the early, dense phases of cosmic evolution. The source of those rays is not a white hole. It is regular matter and radiation following the usual thermodynamic arrow of time. This is the picture that has guided astrophysics ever since. When astronomers in the mid-1960s discovered a bright, flickering source of X-rays in the constellation of Cygnus, later known as Cygnus X1, they were not thinking about eternal diamonds of space-time. They were looking at an object that appeared to be pulling material off a companion star, heating that material in a spiraling accretion flow, and emitting high-energy photons as it did so. By studying the motion of the companion and the properties of the X-ray emission, they inferred the presence of a compact object whose mass was too large and whose size too small to be a white dwarf or a neutron star. The most compelling explanation, developed over years of observation and modeling, was that this system harbored a black hole formed by the collapse of a massive star. It had a birth. It had a history. Matter had fallen in. The horizon, if it existed, did not belong to an eternal, pristine geometry. It belonged to an astrophysical narrative in which a real star in a real galaxy had run out of ways to resist its own gravity. Dozens, and then hundreds, of such candidates accumulated. Some showed up as X-ray binaries, where a normal star orbits a dark companion that siphons off gas. Others revealed themselves through the gravitational waves emitted when two compact objects merged, the ripples in spacetime washing over Earth and briefly jostling the arms of detectors. The heaviest, supermassive black holes lurked in galactic centers, binding stars into fast orbits and powering bright jets. In all of these cases, the evidence points toward objects with formation histories. They grew, they interacted, they accreted. None of them gives even the slightest hint of having sprung out of a past white hole singularity shared with some other universe. On April 10, 2019, this picture took on a new kind of visibility. The Event Horizon Telescope collaboration released the first image of the supermassive black hole at the center of the galaxy, Messier 87, often spoken of as M87 star. Using a network of radio telescopes spread across the Earth, they synthesized a virtual instrument the size of the planet and used it to resolve structure on scales comparable to the black hole's horizon. The image showed a bright, asymmetric ring of emission encircling a dark central depression. That darkness was not the literal surface of a hole, but the shadow cast by the event horizon on the glowing plasma around it. The ring's size and shape matched what general relativity predicts for light orbiting near a spinning black hole of the estimated mass. The surrounding environment, the jets, the accretion flow, the way matter is stirred and heated told a story of an object that has lived in a galaxy for billions of years, feeding on gas and stars. Nothing in that image suggests an eternal, unchanging geometry. Everything about it whispers context. Magnetic fields, turbulent flows, slow growth, long histories. When you take the Oppenheimer-Snyder collapse model as a conceptual template and then overlay it with observations like Cygnus X1 and the M87 star image, a pattern emerges. Black holes in our universe are not platonic shapes floating in a vacuum. They are chapters in the life of matter. They belong to stellar evolution, galactic dynamics, and cosmic history. In the corresponding space-time diagrams, this narrative character has a precise translation. The eternal white hole and the second exterior region that appear in the maximal Schwarzschild extension are cut away. In their place, you have a region of collapsing matter whose world lines begin in a regular past. The event horizon originates at some finite time, as seen by distant observers, wrapping itself around the contracting star. The other universe, on the far side of the bridge, is simply absent. You can still draw something that looks like a Kruskal diagram if you wish, but the lower diamond is now filled in with the physics of collapse, instead of with the vacuum of an eternal white hole. There is only one, asymptotically flat, exterior region. The black hole singularity in the future persists. Penrose's theorems ensure that under broad conditions it must. The past singularity vanishes, replaced by more mundane origins. In this more realistic setting, when you trace outgoing light rays backward, you never find yourself forced to postulate a white hole as their source. Every ray you care about originates in comforting places. The atmosphere of a star, the hot plasma of an accretion disk, the interstellar medium, the early universe. The equations do not compel you to invent a mysterious past singularity to feed the horizon. The matter, content, and cosmic initial conditions you already believe in are enough. This does not mean that the eternal Schwarzschild solution is wrong. It means that it is a special, idealized case, mathematically clean, physically implausible as an exact description of any object with a formation history. It is a bit like the frictionless planes and perfect spheres of introductory mechanics. Useful for building intuition. Potentially misleading if you forget their limitations. If we are honest, this realization trims back some of the most dramatic answers to our original question. The white hole interior and the parallel exterior region that looked so enticing as other sides in the Kruskal picture now appear as artifacts of an idealization. They belong to a space-time that has existed forever and will exist forever, unperturbed by matter fields, rotation, or cosmological expansion. The universe we inhabit, with its hot origin and its evolving galaxies, has no obvious room for such a structure. So what other side remains when we restrict ourselves to collapse-based black holes? There is still the region inside the event horizon, the part of spacetime that no signal can escape from. There is still the future singularity toward which all time-like and null geodesics inside tend in the classical theory. In the Oppenheimer-Snyder picture and in more sophisticated collapse models, the infalling matter and any additional observers who follow it in find their world lines ending at that singular boundary in a finite proper time. From the standpoint of general relativity, this is a real and sobering answer. The guaranteed other side of the horizon is not a bridge to elsewhere. It is the region in which the theory's own description of spacetime fails. The singularity is not a place in the ordinary sense. It is not a location you could visit and take pictures in. It is a limit of the mathematical description, the place where certain curvature invariants diverge, where geodesics cannot be extended any further within the theory. Saying everything ends there is a shorthand for the equations we have break, and we do not yet know what replaces them. Cations. In that sense, the singularity is less a destination and more a boundary in our understanding. It marks the edge of the map. On one side, the geometry is smooth enough that we can talk sensibly about clocks, rulers, light cones, and causal relationships. On the other, our current theory has nothing to say. From the outside, we can never see that boundary directly. All signals from the interior are trapped. We infer its presence from the logic of the field equations and from the generic features of collapse. Penrose's theorems do not tell us what the singularity is made of. They tell us that some form of singular behavior must occur if certain conditions are met. In that way, the future singularity is like a dark punctuation mark at the end of every infalling sentence. If you began this journey hoping that the other side of a black hole would be a vista, another universe, a channel, perhaps a new Big Bang, this answer can feel like a disappointment. It replaces a picture that is visually rich but physically fragile with one that is structurally austere but more honest. It says, "What lies beyond the horizon, in the most robust classical models, is a region where your future ends in a failure of the very mathematics you trusted to describe it." But there is another way to hear this. The fact that general relativity predicts its own breakdown inside black holes is not a mark of defeat. It is a pointer toward the need for a deeper theory, one that can reconcile gravity with quantum mechanics and regulate the infinities that currently appear. In that sense, the singularity is an other side, not in space, but in theory space. It is the place where a new description must eventually take over. The catch is that we have very little observational guidance for what that new description should look like. The horizons of astrophysical black holes are, so far, opaque to us. We can test general relativity just outside them, using gravitational waves and horizon-scale imaging. Those tests, so far, support the classical picture. What happens deep inside remains shielded, both causally and experimentally. Before we confront that quantum unknown more directly, there is one more classical detour we need to take. The black holes we have discussed so far have been non-rotating, the Schwarzschild kind. Real black holes, however, almost certainly spin. Angular momentum changes the interior geometry in ways that our simple collapse models do not capture. In the rotating Kerr solution, the structure of horizons and singularities becomes more elaborate. New types of inner horizons appear. The maximal extension of this spacetime seems to offer, on paper, routes that avoid singularities and connect to other regions. If the eternal Schwarzschild solution tempted us with white holes and bridges we cannot cross, the rotating case tempts us with something more dangerous. Apparent exits that are even harder to dismiss with a simple diagram. To see why those temptations are, once again, likely to be mirages when we bring in physical realism, we have to step into the spinning version of the story. The spinning case feels like a test of everything we have learned so far. How much of the map is physics? And how much is our hunger for escape routes drawn into the margins? Once rotation enters the story, those margins start to shimmer. The simplest black hole solution in general relativity is the Schwarzschild one, the non-rotating, perfectly spherical case we have been quietly leaning on up to now. In that world, there is one horizon, one interior, and one very blunt conclusion about the future of anything that falls in. The next step up in complexity came in the early 1960s, when a mathematician from New Zealand, Roy Kerr, found a new exact solution. In the year 1963, Kerr wrote down the geometry of a rotating black hole. It is hard, from a modern vantage point, to overstate how important that result was. Real astronomical bodies almost never sit in perfect, motionless symmetry. They spin. Stars spin. Galaxies spin. When a massive star collapses, it usually retains some of its angular momentum. There was every reason to expect that real black holes would rotate as well. The Kerr metric gave physicists a way to explore that case with the same mathematical sharpness that Schwarzschild had offered for the static case. The first surprise is that rotation changes not just the details, but the structure. A Kerr black hole has not one, but two horizons. There is an outer event horizon, the familiar surface of no return. Deeper in, there is a second surface, called a Cauchy horizon. The causal structure around that inner horizon is stranger, more delicate. In between, and just outside the outer horizon, lies a region called the ergosphere, where the dragging of spacetime by the spinning mass becomes so strong that no object can remain at rest relative to distant stars. Any time-like world line in that region must rotate with the whole to some degree. The ergosphere is not a horizon. It is a place where the geometry forces you to move, but you can, in principle, still escape if you choose your path carefully. Its existence opens a door to energy extraction processes. In the late 1960s, Roger Penrose proposed a method to tap this rotational energy. Send a particle into the ergosphere. Let it split in such a way that one fragment falls into the black hole with negative energy as measured from infinity, while the other escapes with more energy than the original. The black hole loses a little of its spin. You gain the difference. This Penrose process is a reminder that rotation is not a trivial add-on. It reshapes the regions around the horizon, both physically and conceptually. Inside the outer horizon, the Kerr geometry becomes progressively more exotic. The singularity at the core is no longer a simple point. In the idealized solution, it takes the form of a ring, a loop in spacetime where curvature invariants become infinite. Because the black hole is spinning, the directions in which geodesics can approach and avoid this ring are more varied. Some mathematical paths, in the maximal extension of the Kerr spacetime, seem to thread their way around the singular ring and emerge in new regions beyond. If you draw the full extended diagram for a Kerr black hole with sufficient spin, the structure is lavish. There are multiple asymptotic regions, stacked horizons, and passages that look, on paper, like routes to other universes or other parts of our own. The inner Cauchy horizon acts as a sort of gateway between different domains of predictability. Beyond it, the evolution of fields and particles is no longer fully determined by data on a simple initial surface. The mathematics is telling you that, in this extended spacetime, the classical notion of determinism itself starts to fray. This is the point at which stories about going through the black hole tend to bloom. Sci-fi sketches of rotating black holes often lean on those extended diagrams. They imagine carefully piloted trajectories that dive through the outer horizon, skim the ring's singularity, and pop out in a distant elsewhere, perhaps in another part of the universe, perhaps in a different universe entirely. The presence of the inner horizon and the ring singularity in the Kerr solution seems to offer, at least superficially, more geometric room for such paths than the blunt central singularity of Schwarzschild does. But there is a catch nested inside the Cauchy horizon itself. In the pure, eternal Kerr solution, the Cauchy horizon is a perfectly regular null surface. In that idealized setting, nothing catastrophic happens there. World lines can cross it and continue into the deeper regions of the extended spacetime. The trouble is that this ideal lives on a knife edge. It assumes a level of perfection almost impossible to maintain in a real universe. Exact symmetry, no infalling radiation, no perturbations from external matter, no quantum fluctuations feeding energy into the interior. When physicists began to study what happens to the inner horizon under even tiny departures from ideality, a different picture emerged. The inner horizon turns out to be an amplifier. Small amounts of infalling gravitational radiation, or small irregularities in the collapsing matter, can be exponentially blue-shifted as they approach it. Their energy density in the local frame grows without bound. This effect, sometimes called mass inflation, can transform the Cauchy horizon from a benign surface into a violently singular region. Instead of a smooth gateway to other domains, you get a chaotic, high-curvature wall. Different models and calculations present different levels of severity. And there is an ongoing technical debate about just how strong and generic this instability is. But the broad trend in the literature is clear. The inner horizon of a Kerr black hole is unlikely to remain a gentle crossing in any realistic collapse scenario. The more you feed in perturbations which, in the real universe, are unavoidable, the more that delicate internal structure is shredded. In that sense, the Kerr solution repeats, in a more dramatic key, the lesson we encountered with the white hole and the Einstein-Rosen bridge. The maximal extension of the equations offers an abundance of regions and roots. When you bring in the messy fact that real black holes form from collapse, interact with their environment, and are bathed in radiation, many of those roots pinch off or erupt into singularities. The other sides, that seemed available on paper, are erased by instability. There is an irony here. Kerr black holes are not mere mathematical toys. They are central to modern astrophysics. The black hole at the center of the galaxy Messier 87 appears, from the detailed modeling of the Event Horizon Telescope data, to be spinning. Its shadow and the surrounding emission ring fit best with a rotating geometry. The supermassive object at the center of our own galaxy, Sagittarius A star, shows variability and orbital dynamics of nearby stars that are best explained by a compact, probably rotating mass. Stellar mass black holes formed in supernovae are expected to inherit a substantial fraction of their progenitors' angular momentum. Gravitational wave observations add another layer of evidence. Since the first detection in September of the year 2015, signals from merging black holes have revealed ring-down patterns consistent with spinning Kerr remnants. The quasi-normal mode frequencies measured in these events match. Within uncertainties, the spectrum predicted by the Kerr metric for the masses and spins inferred. Over and over, the universe seems to be telling us, when gravity collapses matter into a black hole, the result is not a static sphere, but a spinning Kerr object. So Kerr is more than a thought experiment. It is, in important ways, the backbone of how we interpret the data. The question is not whether Kerr black holes exist. It is what parts of their maximal extension nature actually uses. Outside the outer horizon, and down to that horizon itself, the evidence so far is that the Kerr description works beautifully. The shapes of shadows, the orbits of stars, the frequencies of gravitational waves, all line up with its predictions. Inside the horizon, where no direct observation can reach, we rely on theory. That theory, when we include realistic perturbations and collapse histories, suggests that the inner Cauchy horizon is unlikely to remain intact. If that is right, then the routes that looked open in the idealized Kerr diagrams are swallowed by a more violent interior structure. The would-be passages that skirt the ring's singularity and leak into other regions are replaced by something closer to a chaotic, singular region where curvature and energy densities soar and our understanding fails. Even if some narrow class of finely tuned initial conditions could preserve a more gentle inner horizon, those conditions would have to be so special, so unlike the messy collapse of real stars and mergers, that betting on them as an answer to what lies on the other side would be a kind of wishful thinking. The cultural story lags behind this technical nuance. Rotating black holes remain a favorite portal device in films and novels. It is easy to see why. They combine all the mood of a black hole, the darkness, the gravity, the sense of an ultimate edge, with the tantalizing complexity of extra horizons and ring singularities. A character can dive into the spinning abyss and, with the right narrative grace, emerge somewhere else. The equations are often invoked as a kind of blessing. General relativity allows it, people say, pointing to the extended Kerr solution. What the equations actually say is quieter and harsher. They say that, in a perfectly symmetric, eternally existing vacuum Kerr spacetime, there are regions beyond the outer event horizon, connected through inner horizons and ring singularities that one can describe in a classical way. They also say that those regions are exquisitely sensitive to perturbations, and that any realistic source of a Kerr black hole will come with enough irregularities to likely destroy the gentle inner structure. They say that rotation is real, that the ergosphere is real, that energy extraction is possible in principle, that horizons of spinning black holes behave in ways we can test near their surfaces. They do not, at our current level of understanding, offer a trustworthy, causal path through to somewhere else that a human could ride. So we find ourselves, once again, in a familiar position. The map permits more than the territory is willing to host. The mathematics, pushed to its maximal extension, draws out elaborate other sides that rely on eternal existence, perfect symmetry, and an absence of perturbations that no object in our universe can enjoy. The physics of collapse, the arrow of time, and the ubiquity of fluctuations step in and quietly erase many of those possibilities. By now, the pattern is hard to ignore. Every time we chase the idea of a black hole's other side through the classical theory, whether through white holes, Einstein-Rosen bridges, or rotating interiors, we eventually run up against the same boundary. The point where the smooth manifold ends, the light cones converge, and the curvature grows without limit. The place where general relativity itself stops speaking. And so, as we approach the end of this journey, the question shifts one last time. Is there anything truly amazing beyond the event horizon in the sense we first imagined, some hidden landscape waiting for us on the far side? Or is the most astonishing fact the one we have been circling all along? That the deepest other side a black hole offers is not a place in space, but the edge of a theory that has otherwise described the universe with uncanny success? Maybe the most unsettling answer is also the simplest one. There really is an other side to a black hole, but it is not a place. It is a silence in our best theory, a place where the equations themselves stop making sense. In every serious model of a black hole we have built so far, the story inside the horizon has the same shape, whether you start from the non-rotating Schwarzschild solution, the spinning Kerr geometry, or a collapse model like Oppenheimer-Snyder. Time-like paths that cross the event horizon do not wander forever. They do not loop around and come back out somewhere else. They head into a region where general relativity predicts that certain measures of curvature grow without bound in a finite amount of proper time. Physicists use the word singularity for that region, but the word can be misleading if you picture it as a tiny, sharp object sitting at the center of space. What the mathematics is really saying is this: along some world lines, the curvature becomes larger and larger without limit, and those world lines cannot be extended any further within the framework of the theory. The geometry, as described by the equations we trust everywhere else, simply fails to continue. The infinite curvature that appears in textbooks is not a detailed image of reality. It is more like a red warning light on the dashboard of the theory, blinking to say, beyond this point, the model you are using has gone out of its domain of validity. It is a limit of a description, not necessarily the literal end of the universe. For a while, that might have seemed like the end of the story. A black hole forms from collapse. An event horizon wraps around it. The interior funnels geodesics toward a singular region where general relativity breaks down. Question closed, at least within the classical theory. Then, in the 1970s, a new ingredient arrived from a different corner of physics. On March 1st, 1974, a short paper appeared in the journal Nature, with a question in its title: Black Hole Explosions? Its author was Stephen Hawking. By combining quantum field theory with the curved spacetime of a black hole background, he argued that black holes should not be perfectly black. When you treat quantum fields near the horizon carefully, you find that particle pairs can be created in such a way that one member falls in and the other escapes to infinity, carrying energy. To a distant observer, the black hole appears to radiate thermally, with a temperature inversely proportional to its mass. This Hawking radiation is wildly feeble for astrophysical black holes. A stellar mass black hole would take far longer than the current age of the universe to evaporate. But conceptually, it was a shock. If black holes radiate, they can, in principle, lose mass. If they lose mass, they can evaporate entirely. And if they evaporate entirely, what happens to the singularity and to whatever fell inside? Does the singular region persist until the last moment and then vanish? Is it somehow resolved by quantum effects long before the evaporation completes? Does the interior pinch off into some separate quantum region while the exterior shrinks away? Our equations do not yet agree on an answer. Hawking's calculation also opened a deeper wound, now known as the black hole information paradox. The radiation he derived is thermal. It depends only on a few coarse properties of the black hole, such as its mass, charge, and spin. It does not carry detailed information about the matter that fell in. If a black hole forms from a complex quantum state, then radiates away thermally and disappears, it seems as though the detailed information about the initial state has been lost from the universe. But in ordinary quantum mechanics, the evolution of a closed system is unitary. Information can be scrambled, but not destroyed. For decades, theoretical physicists have been worrying at this contradiction like a loose thread. Some have suggested that the information is somehow encoded in subtle correlations in the Hawking radiation, even though it looks thermal at first glance. Others have proposed that the horizon is not as smooth as general relativity claims, that there may be a firewall of high-energy excitations there, breaking the equivalence principle to preserve unitarity. Still others have turned to the holographic principle, an idea born from studies of black hole entropy and sharpened by work on anti-de Sitter space and conformal field theory dualities, where certain gravitational systems in higher dimensions can be described entirely by non-gravitational quantum theories on their boundaries. In that holographic view, the interior of a black hole and the information it contains might be encoded in a lower dimensional quantum system living on a distant surface. Geometrical notions like inside and outside become intertwined with patterns of entanglement. The Einstein-Rosen bridges we talked about earlier acquire a possible second life as representations of entangled pairs, leading to speculative slogans like wormholes, equal entanglement. These ideas are beautiful. They are also, as far as black holes in our universe are concerned, largely untested. What we can test lies close to the horizon, not beyond it. The Event Horizon Telescope images of Messier 87 star and of Sagittarius A star probe the spacetime geometry on scales only a few times larger than the event horizon radius. Gravitational wave observations from detectors like the Laser Interferometer Gravitational Wave Observatory in Virgo measure the characteristic ring-down vibrations of newly formed black holes after mergers. In all of these cases, so far, the data tell us that spacetime behaves near the horizon in the way general relativity predicts, at least to within our current uncertainties. We do not see echoes in the gravitational wave signals that would clearly indicate a hard surface instead of a horizon. We do not see obvious deviations in shadow size that would scream, "This is not a black hole." The classical description appears to be doing its job in the regions we can observe. Beyond the horizon, we have no direct access. No light or gravitational wave produced deep inside can propagate out to tell us what happens as curvature grows. Our inferences there are theoretical, not empirical. So we are in an odd position. Outside the event horizon, and right up to it, general relativity passes every test we can perform. Inside, the same theory predicts its own breakdown at singularities. Quantum field theory on curved backgrounds tells us black holes radiate and can evaporate. But when we try to combine that with the classical picture of the interior, we run into paradoxes about information and unitarity. Candidate frameworks for quantum gravity, string theory, loop quantum gravity, holographic dualities, and others offer tantalizing hints that singularities may be resolved, that spacetime might acquire a discrete structure, or that the very notion of geometry might emerge from quantum entanglement. But none of those frameworks has yet delivered a universally accepted, experimentally anchored answer to the specific question: what replaces the classical singularity inside a realistic black hole? This is why it can be helpful to rephrase our original question one last time. Instead of asking, what is on the other side of a black hole? As if we were asking about a country on the far shore of an ocean, we can ask, at what point does our current description of reality stop being trustworthy? And what sort of description might take over? In that sense, the most honest other side we can talk about is not hidden in some distant region of spacetime. It is hidden in the gap between two theories. On one side of that gap is general relativity, a classical field theory that has guided spacecraft, explained the orbits of planets, predicted the existence of gravitational waves, and passed precise tests in the solar system and beyond. On the other side is a hoped-for quantum theory of gravity, still incomplete, that would account for the microscopic structure of spacetime, reconcile singularities with finite physics, and resolve paradoxes like the one Hawking exposed. The event horizon of a black hole plays a double role in this story. Physically, it is a causal boundary. Once you cross it, no future directed path can lead you back out to distant observers. Conceptually, it is a curtain. It hides from external experimenters the details of whatever new physics might live in the interior. Even if tomorrow we wrote down the correct equations of quantum gravity on a blackboard, our ability to test their predictions about singularity, resolution, or interior structure would be severely limited. The cosmos has placed its most extreme gravitational laboratories behind one-way doors. From a narrative point of view, this could be frustrating. There is a strong temptation to invent a picturesque answer to fill the silence. Maybe there is another universe growing inside each singularity. Maybe black holes are seeds of new big bangs. Maybe the interior pinches off into a baby spacetime with its own galaxies and its own arrow of time. These ideas are not impossible. Some have been sketched out in speculative models. But at our current level of evidence, they occupy the same category as the white hole region in the eternal Schwarzschild solution. Possibilities the equations do not rule out, not realities the data require. If we look back over the history of this subject, a quieter pattern emerges. In 1916, Carl Schwarzschild found the first exact solution of Einstein's new field equations and uncovered the radius that would later be associated with black holes. At first, the singular features of that solution were dismissed as coordinate artifacts or mathematical curiosities. In 1939, Oppenheimer and Snyder showed that realistic gravitational collapse would, in fact, form an event horizon and drive matter toward a singular region in finite, proper time. The idea of a black hole moved closer to physical reality, but there was still a tendency to think of it as an extreme endpoint, not a common object. In March of 1974, Hawking's calculation of black hole radiation upended the picture again, showing that black holes have temperatures and entropies and can evaporate, knitting together gravity, thermodynamics, and quantum theory in an unexpected way. In April of 2019, the Event Horizon Telescope turned decades of inference into the first direct image of a black hole shadow, showing that the warped light around an event horizon can be traced with instruments on Earth. Every time the story seemed to be closing when we thought we had the solution, the collapse model, the thermodynamics pinned down, the universe opened a new question about singularities, about evaporation, about information, about quantum structure, about observation. Seen in that light, the most amazing fact about what lies on the other side of a black hole is not that there is a hidden landscape we can describe in comforting detail. It is that there is a boundary in our understanding that refuses to yield to simple pictures. The other side is not a realm of settled answers. It is the place where our best current theory says, "Here I stop," and where our next theory, the one we do not yet fully possess, will have to begin. There is a kind of humility in accepting that. To admit, after more than a century of exploring general relativity and decades of studying black holes, that we do not know what happens to space-time and matter at the deepest interior is not a failure. It is a rare act of intellectual honesty. It is saying, this is as far as our light reaches. Beyond this horizon, we are in the dark, but not without direction. For many people, the word mystery sounds like a soft cushion for ignorance. In the context of black holes, it is something sharper. The mystery here is not that we have not looked hard enough or built big enough telescopes. It is that the universe has combined gravity and quantum mechanics in a regime where our separate tools for each stop working. And it has done so in a way that hides the result from direct view. You could take that as a reason to be disappointed. The video could have ended with a neat answer about wormholes or other universes. It would have been emotionally satisfying, perhaps even wonderful to picture. Instead, the most truthful ending is more narrow and more open at the same time. We can say, with confidence, that in the best classical models, time-like paths inside black holes lead to regions where general relativity breaks down. We can say that quantum effects like Hawking radiation make the fate of that interior even more uncertain. We can say that observations of shadows and gravitational waves support the existence of horizons and the accuracy of general relativity just outside them. Beyond that, we can only gesture at possibilities, constrained by consistency but not yet anchored by experiment. So, if you find yourself still wondering, still turning the question over in your mind after this ends, that is not a bug. It is the point. The honest answer to what is on the other side of a black hole today is that we do not yet know in detail, and that not knowing is precisely what makes black holes such powerful mirrors. They show us where our theories succeed, where they contradict one another, and where they fall silent. They remind us that the universe is under no obligation to reveal all of its structure in one generation or in one lifetime. If anything in this slow journey has stayed with you, the idea of horizons as causal boundaries, the strange maps we draw to tame them, the way singularities mark the edge of our understanding. Let it be this: mystery is not an admission of defeat. It is a boundary condition of being human. We live, all of us, outside the horizon. We send out our questions like light, and some of them come back with answers. Some never return. Black holes are the places where, even in principle, no reply can arrive. That silence is not empty. It is full of the next theory we have not yet written. If you would like to keep walking out to edges like this, where science is clear about what it knows and just as clear about what it cannot yet say, stay with this channel, share this journey with someone who loves the night sky, and let your next question be at least as unreasonable as this one.